Thanks for allowing us to come here and talk about this project. This is something that Hanson has worked on for a number of years. I'll go through the timeline here as we get through the project. This is actually an image of the structure. I have a couple images of that and some 2D images to go through. So real briefly, agenda-wise, the basic point is here I want to show you, a little bit of background, why we did things that we did, what the results were, and how that impacted permitting and design. This is for the McClugage Bridge. So where the heck is that? Just to give you some perspective to where we are today, we're probably about a dead 6 hours west of here. McClugage Bridge is in Peoria, Illinois, which is on the Illinois River. And you can kind of see it there depicted in the Topo map. And here's where the actual bridge is. This is actually kind of more of a local commuter bridge. It's been there for a while. Most of you who might have driven through Illinois, if you were going from north to south and you were going to go through Peoria, you probably would have taken one of two bridges, which one of them is the next one down on the I-74 bridge. A little bit narrower crossing, but still, if you were going to do any local travel, you might have taken this structure. So Hanson formed a joint venture with TY Lin to design this structure for the Illinois Department of Transportation. That's ultimately the owner. Hanson was in charge of the phase one, which in Illinois basically needs all the permitting all the way up through a portion of the design. So we do the TSNL, we set up a lot of the hydraulics, or the entire hydraulic report is done, the structures and geotechnical reports are done by that phase. And then TY Lin really was on for phase two for final design. The estimated design and construction is at $200 million for the bridge. So a little background on the bridge itself. We are replacing only one of those two truss structures. We're replacing the eastbound truss, and it was originally constructed in 1948. It has really outlived its life. It's structurally deficient, and the westbound structure is still good. It was built in the early 80s. The existing structure that we're replacing is, like I said, it's about 5,000 feet long, 47 to 45, 28 spans. It has a 536-foot long navigation span, and actually 411 of that is actually the real true navigation opening, because of course it's on a skew. The bridge from basically abutment to abutment has a variety of structural elements, including the truss itself, which you can mostly see, but then also some steel plate girders, some wide flange beams, and others. The existing bridge itself is fairly narrow, not uncommon for that era of construction. So you might get kind of nervous driving across it. I think the speed is reduced slightly on it because of that, but it is only 33.5 feet wide. Just real quick on the schedule, where we're at. So we've been working on this since 2014, and we've gotten through basically all the NEPA permitting processes, and right now the actual phase two has already started earlier this year, and construction is supposed to start next year. So in just a few months they'll submit final plans for the bridge. A little bit on the Illinois River for those who aren't familiar. Illinois River is the main shipping connection between the Great Lakes and the Gulf of Mexico. It's about 340 miles long, and it has 8 navigation locks on it. And so the bridge itself, if you visualize that from the mouth at Grafton, which is just north of St. Louis, it's about 165 river miles upstream is where the bridge actually is. The total drainage area is about 14,000 square miles to the bridge. And luckily there's a gauge right there, so we have a lot of great information about what's happened in history. And before we started working on it, the bridge actually did suffer its highest flood of record in 2013. It was about 6 inches higher than it had been in the past, which was in the 40s, I believe. And you can kind of see its gauge record there. Just a little bit on the navigation. This is actually a great shot from Wikipedia. I don't know where they got it. I didn't check that far into it, so I'll credit them. But you can see what those elevation differences are in the different lock systems. So it's 160 feet of elevation difference between Lake Michigan and the outlet on the Mississippi River at Grafton. And the kind of drawing on the upper corner there is, they call them the AIS position system. So the Corps of Engineers tracks all the navigation, all the barges that are going through the system are tracked. You can actually query them right now if you wanted to find out where any vessel is. And so this is basically like a heat map. Tells you how they were able to navigate through the channel. So that kind of predominant orange-red sort of line in the center shows you that they're really not having a problem with it. Now in 2013, it does look like someone got a little squirrely. As you approach the bridge, it is kind of actually challenging to see because there's 3 large spans, but only the middle one is the navigation span. It's well documented on the navigation charts, and we had worked with the river navigators to understand whether this was a problem that needed to be addressed during design. Of course, we had to figure out which alignment we were going to go with. Were we going to build the project on the existing alignment? Were we going to build it north of the existing structure, upstream, flowing the images from top to bottom? Or were we going to build it on the south alignment? And ultimately, the preferred alignment was the southern one. And then we had to figure out what type of bridge we were actually going to construct. So for a navigation opening of that size, there are several options. They could build a tied arch structure, a true arch, a cable stay that could go back with a truss, or they could build an extrados or extrados bridge, depending on where you're from. Ultimately, the tied arch was considered the most efficient structure for this crossing, and you can get some depictions here. And then the other thing worth noting is the original bridge was only a little bit more than 35 feet wide, and the new one's almost 75 feet wide and includes full shoulders, 3 lanes of traffic, and a multi-use trail. This is maybe one of the better images of the alignment of the structure and how it would get, how passengers would travel through. In red, it looks a little darker on the downstream side. That's actually where the multi-use path is. It'll be on the river side of the crossing. And then you can see kind of where all the piers are, which are in yellow. This is just from the general plan and elevation for the final drawing. As you can see, the new bridge has 22 piers in total. And here's sort of the main channel area. We call this the group 2 piers. I'll get into that a little bit, but the final bridge has a face-to-face opening of 640 feet. And here's what the piers ultimately look like. You'll see those shapes in the 2D model as we move through that. The one on the actual left has an icebreaker on it. That's what an icebreaker tip, as they call it. And just a little bit of timeline, how we worked through the process. We actually, in 1D, did preliminary modeling is what I would describe that. We put together a model for both the tied arch first, and then we actually looked at a true arch also. We were required to do that. And then we basically immediately started work on the 2D modeling. We had identified that the 2D modeling needed to be considered from the very, very beginning. And ultimately, the final hydraulic report with the final condition was accepted in February of 2018, earlier this year. So nice sections, right? So 1D modeling had to be done first. So I don't have a good floodplain, what FEMA really believes the river floodplain and the floodway looks like here. And that's because there is a county boundary between, it goes right down the river, and actually the Peoria County side has struggled for a long time to accept those maps and is in still a form of acceptance that's not official. So I can't give you that great map you would get from FEMA to show you what's going on there. Actually, the Tazewell County side has accepted that information. So you can use the cross sections as a general idea. That's 500-year floodplain valley, basically. And then the other thing I'm trying to show you is just how we had to skew the cross sections to get close to the bridge so that we could understand just what was going on there. And again, this was intended for not just permitting within Illinois, which I'll get to, but also design. On that same preliminary hydraulics, we had to estimate angles of attack. We had initial project mapping for the river, and without a model, we had to make an initial guess what we thought those angles of attack were using only the topo. So you can see those initial drawings here, and here's kind of a zoom in of some areas, and just how we exactly would model those piers in 1D. The original, we decided, there were several iterations of this, but basically we modeled the 2 existing structures as one and sort of aggregated the piers. The piers in the existing 2 structures don't align hydraulically, which is pretty common. And so we kind of have to look both upstream and downstream and decide what we think the river is actually seeing and how the 1D model should address that. So skew was a very important part to understand, and it was different for every pier. So 1D results. This is kind of hard to see, but I zoomed in towards the top. So this is a navigation section of the river. So the flow velocities are controlled by the dams. And as you can see, where it says velocity channel, at the peak we had, for very low flows, we were just approaching just a little over 1 foot per second. So generally, pretty easy to maybe permit a bridge that has that level of velocity. But when it comes to the 2-year, we were actually surcharging 1/10 of a foot. In Illinois, we have very prescriptive rules for floodway construction, and 1/10 of a foot in this reach is too much. In fact, they don't really use the term no rise in Illinois, but that's a very effective term. Essentially, we had to try to get the bridge to 0. So we were already doing the 2D model. We thought, well, we might get more enlightened solution here on the 2D side. Let's see what happens. And so that's where we headed. The goals were really to look at the permitting and see if the result for that 2-year, for that low flow frequency, actually got a little better. And then we were really interested in what the implications would be with respect to the foundation design, so Scour. So this isn't probably a great graphic at this scale, but you can see where the existing piers are in yellow, maybe if you squint. And then there's where the red ones are, just on a basically full valley section look. And part of what I want you to see here is really kind of looking at the multiple topo sources. So we had 2012 LiDAR that was good for all the dry areas, essentially. And then we had project bathymetry that was done, which included some actually multi-beam data that was collected closer to the main channel. You can see where kind of a higher density section is right around these piers, and you'll see why we were able to get that. And then we had to stitch in a lot of core bathymetry. They pretty regularly survey this section of the river. They have to maintain that 9-foot navigation channel, and so they definitely monitor it, and we were able to utilize their data in addition to ours. They also, right when the project started, the Corps began construction on a planned habitat island that was constructed. This island did not exist when we were going through the initial scoping phases, but it was on the plans, and they were just starting to construct. So we got their final condition bathymetry, and we got their as-built plans, which all had to be stitched into the surface. So here's what it kind of looked like. You could see the LiDAR collection did pick up some of that island when they were constructing it, but ultimately that's what it looked like when we were all said and done. And it wasn't perfect. It absolutely wasn't perfect, but by the time we got done going through the process of meshing everything, we really had a very good modeling surface at the end. So just a little bit about our boundary conditions. We did model this, if I haven't said it before, in SRH 2D. We had identified very early that that was the program to use for a variety of different reasons. Our upstream boundary was an inlet Q, and our downstream boundary was actually an exit H, or we actually put it in as a rating curve. We utilized that option. The Corps of Engineers had done a flow frequency study on the upper Mississippi, which included the Missouri and Illinois River, and had really good data for that here, which you can see in that table. Those are basically the boundary conditions. And just to give you some perspective on discharge, the 100-year was 91,000 CFS. This is probably the only image I have, I think, of the mesh itself. This is straight out of our report. We had lots of topographic things to have to manage, including big scour holes. Actually, this right here is kind of zoomed in over one of the main channel scour holes that was very well formed and required a lot greater density in that general area to get it, because it just wasn't anything consistent, of course. And so we had to increase the resolutions there. So generally around the piers, we had about a 1-foot spacing. We tried to get to within like a buffer area of about 5 foot of spacing on those elements. And in the channel quadrilateral elements, we were back to about 25 feet on average for the crossing. And then in some of the floodplain areas, we could even get up to 200 feet. In the end, we did. I echo the concern about where you start when you start doing meshing. And we initially started out well over 300,000, and we're able to spend a lot of time trying to optimize it, getting it down, checking the sensitivity, trying to get it down, looking at how we could make it operate quicker for us, because we knew we had to throw a lot of what-ifs at it. And ultimately, the existing conditions model got about 93,000 elements, and we were just under 140,000 in final condition. We also ran our own model stability checks. These are actually reports that we run as part of that process. We needed to run the 2 all the way up to the 500-year event, so we did that for existing and proposed. conditions. And because I've not had much luck with videos and PowerPoints, although I do have one here, I couldn't resist. I did just grab some static images of these flow traces. I'm sure most of you who have done some SRH are familiar with these. I do think they capture the general picture here of what we're looking at with respect to the crossing. As we kind of zoom in, we can see how the flow is moving around the piers. And that's a very critical thing to kind of eyeball. It was something we were certainly eyeballing during the process. We wanted to understand how that existing bridge was going to impact the proposed structure. This was an area in particular that we were worried about. We had identified several locations like this where we thought that the water might literally squirt through the existing bridge onto our proposed piers. And in one area, it might not be an issue because there isn't a pier located there. But in this case, there did happen to be one that was in the vicinity. So that was certainly one of the areas we were looking at. We'll see if I can get lucky enough here to present this. Look at that. Of course. Well, anyway, you get the idea. That shows you where some of those negative spaces are, shows you where we're getting recircs, and shows you where the velocity is sort of concentrating. And then the other area we knew we were potentially going to have some issues was on the eastern abutment. There's a lot of floodplain gets blocked by that. That's well in excess of the 500-year. The embankment is on that side, so there's a lot of floodplain that's blocked there. So we were real concerned that maybe, we could see in the topography that there were some depressions there that might have been evidence of some past abutment scour on the structure. And so we're certainly making note of this area. This shows some of our tech plots for what the final condition SRH model looked like. So that shows you the flow traces in the main channel. And then we started to quickly realize that there was a secondary benefit that we were getting to the process, that we could go back and refine our angles of attack. In the original 1D model, all we really had was the topo to look at before we ran it. After the 2D model, we could see those, and in some cases we were able to shallow them up, which was important for the main channels piers where they were larger. And on some of the more approach spans, some of those piers actually got a little worse with the angles of attack. So we were able to sort of true those up, which was important to the process. Then just seeing, you saw what the flow traces were. It seems like there was going to be something drastic happening there, but when you really took a closer look at it, the flow, that pure abutment scour concern that you would have about fast-moving water mixing with slow-moving water, it just wasn't fast enough. As it turns out, you can kind of see on the velocity magnitude there, everything over there that was recirculating was at or close to zero. It was still showing that it was recirculating, but it was just very, very slow. So ultimately, a standard scour protection for abutment to wrap around the abutment in rock was sufficient, and there really wasn't any evidence on the actual infrastructure for the existing bridge that they had ever really had a problem at the structure. So we got an existing model, we got a proposed model. What did it end up mean? Well, we can see here that existing proposed, we were able to sort of debunk the tenth of a foot increase that we got in the 1D model and got that all the way down to 0.004, which, yes, we were looking at it to 0.004. And still are looking at it to that level, as it turns out. But this gives you an idea. Water surface-wise, we think it performed very well with respect to the model in comparison to the 1D. Looking at the scour results. So one of the things that we did here is we were trying to recognize and work with our foundations engineers and structural engineers on the phase 1 part of the project is to address, okay, so we're going to calculate some scour. We can see some evidence of some deep scour that has occurred in these piers. So we were fairly preemptive about it. And one of the things that I think was a solid tool for us and will continue to be is we started to create these maps using the data calculator in SRH, in SMS actually, to take two elements of the two most sensitive elements for scour out of that pier scour equation, the depth and the velocity, and for us extrude as part of the Froude number. And we basically took those two and multiplied them together. So we took the depth raised to the 0.35 times the Froude number to the 0.43, and we multiplied those together and mapped where that was. And as we go through this process, what that helped us look at was where we saw the highest scour potential, right? So on this bridge, this is what we called the group 1. So these are the western piers, the approach from the western side, and we could see that we had the highest velocity kind of right down there where we're seeing those little notes. That one happened to be towards the nose of a proposed pier. But on the main channel, what we saw was that didn't occur till closer, more of what we would consider like an approach section. And on the group 3, the eastern bank, we could see that actually occurred almost kind of right where you would expect it to be, right where that velocity was squirting through those existing piers, which we had seen in some of those flow traces. So that was our approach. But we were concerned that might be too conservative. So what we did was we calculated what we called the peak value. So in that group, we estimated where that peak scour potential factor was. And then we also looked at a more traditional local factor, and we compared them. And you can see right there the actual peak for group 2, so that's the main channel, the Pier 15, that the pier difference was really 7 feet. And when we're talking about 37 feet total, we felt comfortable that it wasn't overly conservative. And some of the approach spans, it was a little bit more percentage-wise, but we still felt like that was a reasonable concern in trying to address any issues associated with the channel being able to shift maybe slightly and maybe attack a pier that it's not attacking now. So ultimately, that was our recommendation. We grouped those piers and we made recommendations for those final scour depths based off of the peak. You can see there, 37 feet for the 100-year. And of course, we mapped it. I gave a presentation 2 years ago about overlapping scour cones on a project we did up in Alaska. So mapping these it's a very important part of the process to understand if your piers, if you start getting deep scour, is it deep enough to actually have those cones overlap? It's a big issue if they do. And so we certainly mapped that. You can see the contraction scour was 4 feet is what we calculated from the 2D model. And you can see how that resulted there. And we actually, with our structural and geotechnical team, we developed this cross-section. And this shows a combination of geotechnical things, including where the bedrock is here down in the red. And then up here, you can see where the ground elevation is, kind of starting from the top. We then dropped everything 4 feet with a scour protection, or for a contraction scour. And then here is where we start to get some consolidated material. So that red dash line is showing that the material is just a little bit more, I don't know if standard's really the right word, because above there it was much more soupy, is the way it was described to me, almost like pudding. So you have to imagine, in the earlier slides when I was showing, we had a very wide section, then it got very narrow, and then it was widening out, right where the bridge was. So we're going into this almost a lake. In fact, they call it Peoria Lake. So there's a sedimentation issue that's pretty well documented on the river itself. And so a lot of unconsolidated materials up above. And what we had recommended was this dark dashed blue line is what we had recommended as those design scour depths. So basically at this point the project is kind of done. We've agreed on all of those things. The hydraulic report's approved. It's moving towards final design. But for this presentation, we wanted to ask ourselves the question, if we didn't have that 2D model, how would the answers have changed? How would 1D, we were using 1D, we certainly had to use it for permitting. How would that have modified things? So we delved into that a little bit. So we went back and recalculated it, and we can see here that based off a standard flow distribution for where we would take the approach sections, this is the max velocity that we saw, 1.32 feet per second. Depth was still about the same. The results from the 1D and 2D didn't really differ that much on actual elevation. And I think I circle it here. So first column is 2D, second column is 1D, and then the third column in those groups is the subtraction of those. So the difference between the 1D moving towards the 2D was 50% greater. So we got 12 more feet. So our number was 37 feet total. And for the 1D model, if we only used that, we calculated just a little under 25 total. So we went back and remapped this, and we looked at it a little closer. Here's what that difference meant, going back and looking at our kind of design graph. What would that have meant to look at it? But it still sort of bothered us, so we went back and took a closer look. Since we had the benefit of the 2D model, we really delved into what the most sensitive component was. So we know that the depth is not changing that much, but there's 40 feet of water there. So even though you're moving only at 1 feet per second or 1.5 feet per second or up to 2.5 feet per second, that number becomes really, really sensitive. So we looked at that, said, where else can we go? So remember, we took our numbers from the 2D model from up here. And that is what gave us the highest velocity. That was the velocity number that you see, the 2.52. And then we go back and we went and looked, where is that? Let's go look at the flow distributions in our original 1D model. And that purple line represents that. And that highest number with the highest depth, which is always how that works, is only 1.66 feet. Still not a huge difference, but still a sensitive variable. So we dug into it even further. And within the model itself, what you had to do was look at the actual velocity inside the existing bridge upstream of our proposed bridge to find 1.7 feet. And that ended up being the highest velocity that we could find. So we went back and recalculated it. And certainly it did close the gap slightly. Instead of it being a 50% increase over the 1D model, it was really about a 30% increase. And ultimately, that draws me towards our conclusion. This is my last slide here. This is what we learned using the 2D model. We understood better how the flow was diverging as it went towards the cross section. So we certainly got a better handle of how things expanded. Things like that island made a big difference. It's intended to be there as a habitat, but it also has an effect on the bridge itself. We also had a way better understanding of angle of attack on the piers. There's really not a good way to look at that in 1D, not on something that's changing like that. And then we were able to map what we think is a good measurement of scour potential across the entire section. And we could really kind of focus in on where those design elements would be important to the overall bridge design. And then ultimately, we got a real good look at how the existing structure had an impact on the proposed bridge with that pier interaction. So if there's one thing I can say here is I think the 1D models, I know we've been hampering on them a lot here at this conference. They certainly have their place and will continue to. The results elevation-wise were not that great, but when it comes to design, I really think you really have to consider certain things like this, angles of attack, other structures that are in the water, other bridges. And when it comes to modeling a series of bridges that are very close together like that, kind of just because you can doesn't mean you should is, I think, the approach I would take. So with that, I'll entertain any questions.
Excellent. Very informative. Thanks, Tony. Any questions for Tony? Can I get to you with a mic?
With the high flow in 2013, did you have any observational information that verified your scour depths?
No. The main scour hole that we saw on the eastern main channel pier, that had existed in a variety of different data sets. The Corps, I wouldn't say surveyed it on a yearly basis, but it seemed like we'd continually been able to see evidence of that it wasn't something that derived purely from that one event. So that was the best information that we had.
Any other questions?
Yeah, thanks. Great presentation, very, very informative. With the multi-beam sonar that you did around the existing piers, was it?
Yeah, they were actually only able to utilize it. The surveyors actually went out there in lower water, and because of that scour hole that was there, that was one of the few places where they were able to get enough depth to collect it. So that's one of the reasons why we had such a good mapping of that one scour hole there. Everywhere else was done with a higher density single beam.
Okay, and the soupy conditions were or the texture that you were able to get in that scour hole area, was that something that helped you in and of itself with the scour, understanding it at all, even independent of the hydraulics, just understanding the texture leading into it? Or
I don't believe that there was a marked difference for that period. You know, they did, so they, as part of the design process, they locate the piers early in a process, and they go out and they do river borings wherever they expect a proposed pier. So there wasn't a river boring for this project that was in the old scour hole.
Anyone else? Okay. Will's got a question.
So first off, thank you. Also, when you were given the location of the upstream existing bridges, was there any consideration of scour? You have hydraulic impacts that you evaluated here. Did you check the existing bridges scour potential to see if that overlapped with your proposed structure?
So kind of two responses I have to that is the DOT did request that since we were constructing all of these models associated with it, that we do assess the existing structure for scour. I didn't actually populate the item 113. I think the hydraulic engineer for the district actually did utilize our information for that, but they were really looking for something actionable. They wanted to know if when they build the other bridge, should we be dumping rock around the piers on the existing bridge? And so it was part of our intent to quantify the scour to then work towards an actual countermeasure design for those existing piers. But as it turns out, this is just an interesting little fact about the construction side of it, is they actually don't believe that they can construct the bridge by building a causeway. And the reason that they don't believe that they can do that is because that material is so soupy on the approaches that there's no amount of rock. This was the quote from our geotechnical lead. There's no amount of rock I could put in that river that we will be able to find later. So everything, they're going to actually have to probably dredge a channel and then float in barges to pick the spans up on the approaches, and whether they float in the main span or not is still kind of part of it. But all of that material itself was just not solid enough to be able to actually dump that rock. So when it comes to countermeasures, that was one of the things. We normally have a little bit of a belt and suspenders approach. The foundations on the new bridge are designed to be without any countermeasures, and certainly many of them are actually going to be end-bearing on the bedrock down there. So the DOT decided that because we can't really come up with an adequate design for those countermeasures for the proposed bridge, that we probably don't need to put them on the existing either. So.
What material gradation did you use for your scour analysis?
I'd have to.
Was it cohesive material?
It was, yes.
Thanks, Tony.
All right, thank you.